All right, our problem reads, at the county fair, Katie tries her hand at the ring the bell attraction. In this game, the player hits a platform with a mallet. On the platform, a ball sits and it's shot straight upward. If the ball hits the bell situated above, then the player wins a prize. She swings the mallet hard enough to give the ball an initial upward speed of 8 meters per second. Will the ball ring the bell 3 meters from the bottom? Okay, so let's just draw our picture so we can see what that attraction might look like. So here's the platform that the ball is, and here's the bell. It's one of those kind of bells that, you know, looks like a ring. Okay, so when she hits her hammer to the platform, it launches the ball straight up. All right, so not the best picture, but I think you get the idea. Okay, so we have some motion going on. We have an initial velocity. We could do forces and analysis and one-dimensional motion, but we don't have to because we have the power of energy, so we can use energy. And we're going to remind ourselves that we know that the total energy of a system, initial, is equal to the total energy of that system at any other point in time. We'll call that final. So what's our initial and what's our final and what's our system? So the system, well, what objects are involved in this particular motion that we're analyzing? Well, it's the ball. The ball's sort of flying up. So our system, in this case, is just the ball. All right. Now, what's the initial and what's the final? What do we want to call time point 1? And what do we want to call time point 2? Because energy is the same in all of them. Let's say that the initial is when the ball leaves the platform. And our final is when it hits the bell. If it hits the bell. So will it hit the bell? It's really asking, will the bell ring? So if it hits the bell, the final is at the peak or on the way up. Okay, so if it doesn't get to the bell, doesn't get to its peak, it's not going to hit the bell. If it's going fast enough to get to the peak, or to get to the bell, it'll hit the peak. And if it doesn't, or if it just hits the bell, it'll be at the peak. So that's sort of that final condition at the level of the bell. Where would it be when that energy state is that? Okay, we know that the bell is 3 meters high. So the question really being asked is, how high does the ball go? And is it more than 3 meters or less than 3 meters if its initial condition is met? So what type of energy does the ball have at the beginning when it leaves the platform? Well, remember with energy, we have to set sort of that height level of 0. So let's set the height level of 0 when we're at the platform, or at the platform level, not when we are, but at the platform level. All right, so we'll now look at our energy, our possible energies. We have, in our discussion, we have gravitational potential energy, we have kinetic energy, and we have that spring potential energy. And we know that all those added together initially have to equal all of those added together in the final state. So our spring and gravitational potential energy and our kinetic energy. Now, there's no spring involved, so those energies are 0. At the beginning, our height is equal to 0, so our initial potential energy is 0. So at the beginning, we're left just with kinetic energy. And if I want to know how high the ball would go with this state of kinetic energy, I could solve this problem that way. What would be my final height when the ball reaches the top? And when the ball reaches the top, at the peak of motion, the kinetic energy is 0. So I could solve for what is its peak of motion and compare it to my 3 meters. So my initial kinetic energy is going to have to equal my final potential energy. All right, so kinetic energy initial is 1/2 mass times initial velocity, or speed, squared. And my initial potential energy is mass times g times the height, final. Well, my two masses are going to cancel out. And I'm going to solve for height final, so I bring my g over, the initial squared, all divided by g, is equal to my final height. So we have 1/2. We're given that the initial speed is 8 squared over 9.8, and that equals my final height. So 5 times 8 times 8 divided by 9.8 gives me 3.26 meters, which is greater than 3 meters, so the bell rings. All right, so in one fell swoop, we've got our energy relationship. We don't have to do anything with regard to motion and all those variables and steps. So pretty straightforward when we use energy. All right, good job.